Good evening, everyone. It is 3 a.m. in the Philippines as of the moment, and thank you all for inviting me for my presentation. I am Hannah. I am from the Philippines, and it is my honor to present to you our study where we created a decision support system for the optimal allocation and distribution of COVID-19 vaccines using analytic hierarchy process and integer programming models. Before I jump off to the mathy part, let me first show you a picture. And I think for people who came from third world countries, this is very familiar. During the first few weeks of vaccination in the Philippines, vaccination sites were packed to the brim with people. The Philippines Department of Health had assigned prioritization categories by then, but even with this enforced, an unprecedented number of people flooded the vaccination sites and onto the streets. Community quarantine and social distancing requirements have been incessantly violated, all because of the people's efforts to be vaccinated, and we could not question them for that. Now, the National Immunization Team of the Philippines did determine which regions should be prioritized, but their indicators do not apply to municipalities, cities, or communities whose population is less than 100,000. And in the Philippines, there are many communities who do not qualify for this requirement. This is where the challenge is posed. Even when vaccines are abundant now, reaching the vaccination target is a challenge because the LGUs in the Philippines do not have a tool to assign individuals where logistical concerns are answered. These logistical concerns are limited vaccination site capacity, people unwilling to get vaccinated due to transportation concerns, very big supply-demand gap, and local governments differ in prioritization preferences for vaccination sites in their areas. This is also something that we found while reviewing literature, is that while there are many attempts to model the optimal allocation of vaccines for the vaccination rollout, some of these models, or most of these models, do not actually incorporate the differing vaccination strategies of communities or health decision makers of communities. For example, an urbanized region A health decision maker may choose this prioritization strategy, while the rural health decision maker will not choose this prioritization strategy. Now, with this, LGUs have devised their own way of assigning target individuals to vaccination sites, but since these methods are manual, I'm talking about manual paper listing methods, big spreadsheets of Excel, they are time-consuming, potentially inconsistent, and actually very open to bias. To solve this, we incorporated the aforementioned logistical constraints by developing a location allocation model which not only assigns individuals to vaccination centers, but can also tailor the vaccination rollout to prioritize individuals depending on the LGU's preferences and the COVID-19 situation in their areas. How did we do it? We made use of the powerful combination of AHP and IP. Now, AHP here is used to allow LGU-specific prioritization of communities or barangays. Barangays in the Philippines are like wards. They are the subset of cities. And integer programming was used to determine where an individual should be assigned for vaccination. Now, let's take a closer look into these methods. First, for the analytical hierarchy process, the goal is to determine which of these barangays should be prioritized first in the vaccination rollout. The criteria is determined by consultations and correspondence from health decision makers all over the Philippines, where the number of active COVID-19 cases, the population density of a barangay or a community, and the distance of the community to the vaccination site. Now, the LGU decision makers may compare which of these criteria is more important than the other using, of course, SATI scale of relative importance. Now, into the integer programming model, we created this to determine how many vaccine stations to open, considering the target individuals to be vaccinated for each barangay. And this also maximizes the number of individuals to be vaccinated using the weights calculated by the AHP. A closer look on this Here, on the objective function, we try to maximize the AHP-derived prioritization score of communities in the vaccination rollout and assigning the individuals to vaccination sites. This objective function is constrained by 1. The number of individuals to be vaccinated from a barangay should not exceed the target. We also have a capacity constraint, target or the vaccine supply constraint against supply, where we try to not exceed the supply of vaccines when we assign individuals, and the vaccine supply constraint against capacity, meaning the people we try to vaccinate should not exceed the capacity of the vaccines or the supply of the vaccines that we are having. Lastly is the non-negative integer constraint. After all, there is no person who is a decimal or is a negative. And actually, now that we have the AHP-IP model in mind, how do we interpret this so that the LGU user may be able to use this? LGU users typically do not know how to solve AHP-IP models. So we answer this by creating a decision support system. The AHP-IP framework we implemented in this study is implemented in the web-based decision support system that is readily accessible online for decision makers of local government units, where they may be able to come up with a COVID-19 vaccination rollout for their areas. This DSS has 3 main components, or as we'd like to call it, 3 main role players. First is the LGU user. The LGU user supplies master lists. These master lists are 1, individual master lists. This contain the name of the individuals, basic details, what communities they came from. The LGU user would also be providing the AHP scores and the vaccination details, including the date of their vaccine rollout, how long their vaccine rollout would be, the number of people who would be participating in the vaccine rollout, and the brand of the vaccines that they would be using. Now that the vaccine rollout DSS already has these details, it taps onto our AWS database, where we store data on distance, the number of cases or active COVID-19 cases of the barangays, and the population density of the barangay. With these data complete, the vaccine rollout decision support system now creates the vaccination schedule master list, which it would be presenting as a PDF to the LGU user. Our front end has been created using CodeIgniter framework, while the backend utilizes Python's Pulp library. Pulp library is a linear programming model for solving linear problems. And this is a short summary of our backend process. First, the Python script of the system obtains vaccination details. And then second, the prioritization of communities from the target individuals is calculated based on the AHP weights provided by the user. When parameters and variables are populated, the IP model is run using the Pulp library in Python, and the Python generates results. Now the system proceeds to create the vaccine or the whole schedule master list based on the results given by the Pulp library. So our DSS is hosted on a page containing 4 form pages. The second of which has 2 prominent features. First is our AHP scoring panel, where the LGU user would be scoring the pairwise comparison table. Scores are automatically reciprocated on the other side of the diagonal. Second is the preset pairwise comparisons. We already know that decision makers have quite a little problem deciding or solving for consistency ratios or satisfying consistency ratios. So to aid in the judgments and for the convenience of the local government unit user, we present 4 scenarios in the prioritization of communities as presets. So they may use these presets in case these apply to the COVID-19 situation in their areas. First, all equal. All criteria are equally important. Then we have density is very strongly important. Cases or the number of active cases is very strongly important. And lastly, distance, where the distance from the vaccination site is strongly important. The matrix looks like this for each of them. Okay, with that said, we also have a consistency index checker. So when the user has a CI that is greater than 0.10, we know that the decisions are inconsistent. So we try, or in the decision support system, the next button and the lower right panel is disabled until the CI is consistent. So this part of the panel returns the CI value and advises the user to review scores until the CI is lesser than 0.10. Okay. On the third page, we have the master lists form. This part is a master list template download and master list upload, and we also have an error display panel. This panel displays features or displays error checking functionality. It shows number of empty cells, format mistakes, and the existence of headers in the master lists, all of which, if not settled, would not run the model properly. And until these are settled, the next button will be disabled. For the results, as a case study, we considered a small municipality Z whose decision maker aims to vaccinate these individuals from 10 of its communities in a span of 2 days. The municipality has 4 functioning vaccine stations, which are labeled as VSA, B, C, and D. So we assume here that the decision maker is using density or preset 4, where distance is deemed very strongly important. So when this information is input in the DSS, the summary page returns this picture. Please note that here, the preference vector obtained from the user scores of the pairwise comparison matrix for criteria are shown on the card where barangays of vaccination centers are present. Next, when we click the Create Vaccine Schedule, the DSS returns this PDF form. The vaccine rollout schedule generated by the DSS for Municipality Z has successfully assigned all individuals of the communities to the vaccination stations in a 2-day timeline. So since we are running on preset 4, as expected, communities or barangays closer to the vaccine sites are prioritized, since we are under the premise that distance is very strongly important and all constraints are satisfied. We also run a validation test. So a quick look at the results of the model when run in Excel using Solver shows that it is consistent with the results produced by the vaccination DSS. Also, for the AHP calculations, results derived by the DSS also prove to be consistent with results from super decisions. And for our conclusions, we found out that the DSS implements, or in this study, the DSS implements a model that is systematic and consistent, even when confronted with the unique COVID-19 situation of a municipality, where LGUs may be able to come up with a vaccine rollout schedule for their communities in less than 10 minutes. Furthermore, we were able to address these issues. Hence, this DSS potentially outperforms conventional and time-consuming manual decision-making processes currently being used by the local government units. However, we do have limitations. The decision, for example, for choosing the criteria of the AHP model presented in the study came from consultations with local government units in the Philippines who mostly oversees rural areas. So maybe health decision makers of urban areas may have other factors to consider aside from the criteria we mentioned. Also, at the moment, developments in the model to determine which of the individuals in the community should be prioritized are still underway. At the moment, we are currently prioritizing communities, and then we view the individuals in the communities to have the same priority. It might also be interesting to further enhance the functionality of the current DSS to include scheduling and auto SMS features. Lastly, this study only focuses on addressing vaccine deployment. Overall success of the vaccination campaign is still dependent on other epidemiological contexts. And here are our references. And in this work, we would like to honor the life and memory of our dear colleague, Raymond Pailaga, who succumbed to COVID-19 and whose brilliant mind contributed to the development of this paper. This work is supported by the Department of Science and Technology through Project PIPA Stall under the NICER for R&D program. And that's it for my presentation. I would like to open the floor for questions, suggestions, and other information.
Thank you. That was most interesting. Do we have some questions?
I would just like to compliment Hannah. That's a really beautiful study, and your presentation of it was excellent too. Thank you so much for this.
Thank you very much.
I do have a question. You showed the number of people waiting to be vaccinated. That was impressive. How did the people in the Philippines respond to the vaccination? Did they want it, or were there anti-vaxxers who didn't want it? What was that like?
That is actually a very interesting question. There are people in the Philippines who did not want to get vaccinated, but it is I think very small number. Most of them actually in the first few days of the vaccination rollout, it was really crowded in the streets. I remember we were still on very high there were still very high quarantine restrictions, but the streets were flooding with people. I think they were all really wanting to get vaccinated at some point. And at that moment, we found out the DOST, or the Department of Science of the Philippines, knocked on our doors of our university and asked us to help them create this decision support system.
It's really great. Well, thank you so much. Good luck. I hope that you can roll this out.
It is actually already rolled out. We were able to conduct alpha and beta tests, and we did the launching last month.
Wow.
That is just great. Well, thank you again, Hannah.
Thank you,
Luis,
very
I
much.
think that you had the question.
Yes, congratulations, excellent work. And I can see that the front end of your application is very functional. So you solve many important elements of decision making, especially in this remote sentence. So congratulations on that end. But I have just a couple of questions about the implementation of the IP algorithm, because there are some limits that depend on the number of alternative cases you can handle effectively with methods such as branch and bound, or also that constrains and limits the applicability, especially if you have a large number of sites or alternatives. So what are the limitations of that Python library? Because also you can solve it through genetic algorithms or something like that, if that is the case. And also just adding, if you have considered to have a multi-objective programming, like including in your application something like cost or some other restrictions or objectives. So I would like to hear about you, and congratulations again, excellent work.
Thank you, Luis. I think those concerns are very well founded. First off, I would like to address the limitations of the Python model when implemented. I mean, limitations of the IP model when implemented in Python. Python, or the pulp library in Python, actually runs on branch and bound, like the Excel solver. Probably one limitation we found is that, for example, if there was one time we tried to run the entire population of the Philippines using the model, and it took around 30 minutes to run it on the website. So it really takes time. That's why we suggested that this model be implemented, or how do I say? I mean, our website should be given to regions instead of the entire Philippines, so that we could limit the runtime of the Python when running. And also, considerations for the integer programming model. I think we have already plans for it from our beta testing. That is right. The regions or the health decision makers also asked or requested that we incorporate costs and cost constraints. There were also human resource constraints. They were also asking for the AHP matrix to be simplified, which we are still looking into. And we will be, since our research center is still on the second phase of running, we would be trying to implement those on next year.
Thank you.
Thank you very much as well.
All
Do we
right.
have other questions? Before I forget, I would like to thank the committee of the ISAHP for awarding me a student scholarship. Without that, I would not be able to come here at all. Thank you very much.
It would have been our loss if we didn't tap you. It was great.
Definitely. I think that it was really, really worth it. And you did an excellent presentation. So be proud of it.
I would be. Thank you very much.